Welcome back to the deep dive. Today we are cracking open one of those really dense strategic technology blueprints that, chart a course for an entire industry over decades.
We are. We're looking at the very foundation of the intelligent vehicle,
Yeah,
the Electronic and Electrical Information Architecture, or EEI.
right, the EEI. And this isn't just a technical spec sheet. We're doing a consultancy-style deep dive into what's called the EEI RoadMap 3.0.
Exactly. This is the plan that lays out the ambitious, sometimes staggering path for automotive tech all the way through 2040. It's a complete overhaul.
So our mission today is to distill this massive blueprint. We want to understand where the industry is right now, what the critical gaps are, the Achilles heel, really, and then look at the revolutionary goals for the next 15 years.
And this is for you, the listener who wants to go deeper than just the headlines about self-driving cars and really grasp the core strategy behind it all.
Okay, so let's start with the name itself. I've always heard EEA for Electrical and Electronics Architecture. Now it's EEI. Why the change? What does that I for information really signify?
That's a fantastic place to start because that one letter signals a profound strategic shift. The information part emphasizes that this is no longer just about wiring components together.
It's about data.
It's all about deep data fusion. We're talking about three distinct domains of information flow. First, data within the vehicle itself.
Okay.
Second, data between the vehicle and the world around it, vehicle to road, or V2R, vehicle to pedestrian, V2P. And third, a massive constant exchange of data with the cloud.
So EEI is about making that data flow seamless across the physical boundary of the car.
Precisely. It's an information architecture, not just a component architecture.
And this shift, it's so important that the source material says it supports four massive strategic pillars. This isn't just a minor upgrade, is it?
Not at all. These are systemic, even national level drivers. The first pillar is huge, supporting the national transport strategy.
So this is bigger than just making one car smarter.
Much bigger. EEI is the fundamental enabler for high-level autonomous driving L4, L5. But even more than that, it provides the V2V, V2R connectivity that's the absolute bedrock for building a truly smart, efficient national traffic system.
You're moving from optimizing a car to optimizing the traffic flow of an entire city.
Exactly.
Okay, so national infrastructure is one. What about the green targets everyone's talking about?
That's pillar two, achieving dual carbon goals. We always think about the battery, but EEI is critical for efficiency.
Costa.
A smarter car is just a more efficient car. EEI allows for incredibly refined energy management, intelligent power distribution, and crucially, by talking to the cloud and the road, it can optimize driving behavior like predictive cruising, which directly cuts energy use across the entire fleet.
Makes sense. And as these cars become, data centers on wheels, security has to be a major
A
concern.
massive one. That's pillar three. Ensuring industry chain security. As we get more dependent on these powerful computer chips, developing them yourself becomes a strategic necessity.
To reduce reliance on foreign tech.
Right. But it's also about building an architecture that is cyber resilient from the ground up. You have to protect against attacks and manage enormous amounts of sensitive data. It's a national security issue.
Security is a core design principle, not a feature you add later. And the fourth pillar, the economic one.
That's promoting industry transformation. EEI is the engine. When you build a world-class EEI platform, it pulls the whole ecosystem up with it.
What do you mean by that?
You create huge demand for advanced chips, for sophisticated software, for new lightweight materials, for communications tech. It drives investment into high-value, intelligent sectors of the economy.
That's a staggering mandate. It's really about shaping national competitive advantage for decades. Okay, let's unpack this. The blueprint is organized around a framework they call 1 + 3 + 1. What does that mean?
It's just a logical way to break the whole system down. The first one is the foundation, the architecture system itself, the design philosophy.
Okay.
The three in the middle is the functional core, hardware, software, and communication architecture.
The brains, the soul, and the nervous system.
A good way to put it. And that final one is all about quality control, simulation, testing, and evaluation. We're going to dive into the goals for all five of these, right through 2040.
Before we sprint toward that 2040 vision, let's ground ourselves in today. This is RoadMap 3.0, so there was a 2.0 with targets for 2025. How did the industry actually do?
Well, the 2023 status report shows some pretty rapid success, especially on the hardware side.
Like what specifically?
For the architecture platform, they basically hit the goal. The shift to a domain controller-based architecture, using Ethernet as the main backbone network, that's been largely met in new vehicles. Domestic domain controllers are now a reality.
So the physical skeleton and the main arteries are in place. What about the compute power?
Also, good progress there. On the computing platform, they're generally supporting L2 autonomous driving. The energy efficiency is at a decent baseline, around 2 TOPS per watt, and we're seeing the first domestic autonomous operating systems building their own ecosystems.
And the basic wiring and connectors.
The supply chain for those basic components is pretty much established, so a lot of the foundational hardware goals were met.
Okay, so if the hardware, the compute, the basic platform, if all that is mostly on track, where's the big failure? What was the critical gap that makes this new 3.0 roadmap so incredibly aggressive?
It's one single area, and it's the one that's holding the entire system back. It's in what you could call soft power, the maturity, and more importantly, the widespread use of domestic automotive middleware.
Middleware, let's define that. That's the software layer that sits between the applications, the self-driving algorithms, and the actual hardware, the chips, right?
Exactly, it's the translator. And the specific problem is the lack of a complete standardized domestic equivalent to the global AutoSAR software system.
Why is that one missing piece such a huge strategic problem?
Because without standardized middleware, you can't have scale. You can't have interoperability. International competitors lead because they have these mature, standardized ecosystems. We've built fantastic custom hardware, but we're lacking the common language to make it all work together efficiently.
The source material frames this as more than just a technical problem. It calls it the self-reinforcing negative cycle. That sounds systemic.
It is. And this insight is what drives the entire strategy for RoadMap 3.0. It's not a technology problem, it's a structural one.
Okay, so break down this negative cycle for us.
It starts with weakness one, a lack of standardized interfaces. Because there's no common language, no open standard, every single automaker is forced to develop their own proprietary software stack.
Which right away sounds incredibly inefficient.
It leads directly to weakness two, market fragmentation. If you're a supplier making a sensor or a controller, you can't just build one product. You have to spend a fortune customizing it for a dozen different bespoke systems.
So they can't get economies of scale. They're stuck doing low-volume, high-cost custom work.
Precisely. And that fragmentation then creates the third and most critical weakness. It starves the entire ecosystem of data. That's weakness three. If every car is collecting road data using a slightly different proprietary system, you can't aggregate that data easily. You can't normalize it. It's like trying to build a global library where every book is in a unique secret language.
And you can't train a world-class autonomous driving AI if your data is a complete mess.
You absolutely cannot. So breaking this cycle, forcing the industry toward open standards, is the #1 strategic goal. It's about building an ecosystem, not just better tech.
That makes perfect sense. So with that urgency in mind, let's look at the destination, the 2040 vision. The roadmap lays out a 4-stage evolution.
Right. We started at stage 1, the old distributed architecture. Hundreds of little computers, miles of wiring, a nightmare.
Then we moved to stage 2, domain centralized, which was an improvement. And right now, the whole industry is basically at stage 3, central compute plus zone control.
That's the current trend, yes. A big central brain for the heavy lifting like autonomy, with smaller zone controllers managing things locally. But the ultimate 2040 goal is stage 4.
Which is the vehicle cloud centralized architecture. What does that actually mean? It sounds like a huge leap.
It is the paradigm shift. It means the bulk of the heavy computation is offloaded to the cloud. The computer inside the car gets smaller, more specialized.
So what does the in-vehicle computer do then?
It focuses on 2 vital functions. First, mixed criticality scheduling. It has to be brilliant at prioritizing. A command to brake is infinitely more important than streaming a video, and the system has to manage that flawlessly.
Okay, so safety critical tasks are #1. What's the second function?
Full elastic compute allocation. Think of it like a server on wheels. The car doesn't have a fixed amount of processing power. If it encounters a complex, novel situation on the road, it can instantly pull more processing power from the cloud on demand.
That is an incredible level of flexibility. But to get there, the development speed has to accelerate like crazy. The roadmap lays this out in 3 phases.
And that development cycle time is the key metric. It's the ultimate measure of competitive advantage.
So let's start with the near term. The 2030 goal is technology lead.
Right. By 2030, the tech itself has to be world-leading. The architecture is fully central compute plus zone. And here's the kicker. The development time for a new vehicle architecture has to be cut to just 4 months.
4 months. When it used to take, what, 5 years?
Exactly. It's a revolution in how you design a car.
It's already mind-boggling.
What's next?
The midterm goal for 2035 is product lead.
This is about turning that tech leadership into dominant products. The vehicle cloud connection becomes really efficient, and we see the beginnings of that elastic compute allocation, and the target shrinks again.
How much?
New architecture development time, just 2 months.
2 months. That's not even a development cycle anymore. That's almost continuous evolution. Which brings us to the long-term 2040 goal, industry lead.
This is the end state. The vehicle cloud architecture is fully realized. Mass computation happens in the cloud, and the efficiency target hits its peak. A new architecture developed in a single 1 month.
1 month. That single number says everything about the scale of this transformation. It's moving the auto industry to the speed of software.
That's the goal.
Okay, so we have the macro vision. Let's drill down into the 5 pillars, starting with pillar 1, the architecture system. This is the how the design methodology.
Yes, and the core trend here is a big one. It's moving away from the slow, sequential waterfall development process to a combination of model-based systems engineering, MBSE, and agile development.
MBSE. So that's about building a complete digital model of the car's systems before you even touch any hardware.
Exactly. You can simulate everything, data flows, interactions, super early in the process, which saves a massive amount of time and rework. Then you combine that with Agile's rapid iterative development sprints.
But how do you do Agile, which is all about constant change, in a safety-critical system like a car? That seems like a huge tension.
It's the central challenge. The roadmap aims to solve it with AI-driven design. The goal for a new feature, from idea to being in the car, drops from 3 months in 2030 to just 1 week by 2040.
Kind of weak.
AI will automate a lot of the low-level design and coding, which makes that speed possible, and this all ties into the diagnostics piece too.
The vehicle needs to be able to diagnose and fix itself, right?
It has to. By 2040, the goal is a fault detection rate of over 99%, with the cloud gaining the ability to perform remote repairs. A bug gets fixed overnight with a software patch. No trip to the dealer.
That's revolutionary. But what are the big barriers to getting there? It sounds like a massive organizational shift.
It is. The first barrier is that tension you mentioned. Mixing Agile with the strict validation of waterfall processes is really, really hard. Second, there just aren't a lot of proven large-scale examples of MBSE in the auto industry yet.
And it all comes down to the people.
It always does. The biggest barrier is a severe shortage of cross-disciplinary talent. You need engineers who are experts in systems, architecture, software, hardware, and cloud services all at once. They're incredibly rare.
A complete re-engineering of the workforce. Okay, let's pivot to pillar 2. The hardware architecture. The physical brains and nerves of the car.
Right. And the trend here is just relentless simplification and integration.
Today's cars have, what, 5 to 10 domain controllers? Where's that number headed?
The goal is extreme integration. By 2030, a vehicle should run on just 2 or 3 core heterogeneous chips. By 2040, the goal is to have all the high-level computing done on just 1 or 2 core chips.
So you're consolidating the physical chips, but I assume the power of those remaining chips has to go through the roof?
Astronomical leaps. The compute power target is 1 kTOPS, that's 1,000 trillion operations per second by 2030, and it climbs to 2 kTOPS by 2040.
That's basically supercomputer-level performance in a car.
It is. And to do that efficiently, they'll use new tech like chiplets making big chips out of smaller modular ones and in-memory computing to boost speed.
But I saw something interesting in the source. The target for raw CPU power, measured in DMIPS, actually goes down by 2040. Why would that be?
That's the tell. That is the smoking gun that confirms the vehicle cloud centralized strategy. The car is actively shedding the need for high-level, generalized processing.
It's offloading it to the cloud?
Exactly. The local chip focuses on real-time sensor processing, that's the high TOPS number, and executing safety-critical functions. The really heavy thinking happens in the cloud.
That is a fundamental shift. Now, what about the electrical system itself? You mentioned the green pillar. This requires a move away from old-fashioned fuses.
A total digital transformation of power. The shift is to electronic fuses, or e-fuses. They replace physical fuses and relays.
And that lets you control the power grid with software.
Precisely. You can measure current, detect faults instantly, and even reconfigure the power system with an update. The target for 2040 is that 95% of all power sources are smart and controllable.
And this needs a more robust low-voltage system than the old 12-volt standard.
Absolutely. The move to a 48V system is essential to power all these new components efficiently. And that 48V system is also key to the big goal in wiring, which is weight reduction.
Right, the goal of aluminum replacing copper.
Exactly. Lighter wires mean a more efficient vehicle. The weight reduction targets are aggressive, over 17% by 2030 and more than 33% by 2040.
So what's stopping all this hardware evolution right now?
Two things: high cost and a lack of domestic supply for the really advanced components,
Yeah.
like the eFuse chips and the 48V management silicon. And secondly, that old problem comes back: non-unified interfaces between controllers, which prevents suppliers from scaling up.
It all comes back to standardization.
Every single time.
Okay, let's move up the stack to pillar 3. Software architecture. If the hardware is the brain, this is how the brain actually thinks and learns.
Right. The current foundation is service-oriented architecture, or SOA, but it's evolving.
How so?
It's moving toward much finer-grained microservices. So instead of one big chunk of code for autonomous driving, you break it down into tiny independent services. One for sensing, one for planning, one for acting.
And because they're independent, you can update them one by one without breaking the whole system.
Exactly. It allows for continuous development and much better safety redundancy. It's a concept borrowed heavily from modern cloud computing.
And the roadmap leans into that, right? With cloud native and virtualization.
It does. The industry is moving to containerization, things like Docker and Kubernetes. The goal is to completely separate software development from the physical hardware. By 2040, the target is for 80% of all software development and testing to be done in a virtual environment.
That's how you get to a 1-month development cycle. You're not waiting for physical prototypes.
You're not. But again, none of it works at scale without standardization.
What's the target there?
It's extremely high. 80% standardization of service interfaces by 2030 and 90% by 2035. The end goal is a single, unified middleware that works across the vehicle, the cloud, and any hardware, creating a massive shared developer community.
Getting competitors to agree to 90% standardization seems almost impossible.
It's the biggest hurdle. The complexity is immense, and the inertia of proprietary systems is powerful. It's a long, difficult process to get that kind of industry-wide consensus.
If we connect this to the bigger picture, none of this works without a super fast Nova system. Let's get to pillar 4, the communication architecture.
Right. The old standards like CAN bus, which maxes out at 1 megabit per second, are ancient history. They're a huge bottleneck when you're dealing with gigabytes of data from LiDAR and high-res cameras.
So what's the replacement?
The future is all Ethernet and optical communication. Automotive Ethernet is the new backbone, but even that has its limits.
How fast are we talking? What are the targets?
The speeds are staggering. By 2030, we're looking at 1 to 10 gigabits inside the car. That jumps to 10 to 30 gigabits by 2035.
And by 2040?
The target is 30 to 50 gigabits.
50 gigabits per second inside a car. Can you even do that with copper wires with all the electromagnetic interference?
You can't. Not reliably. Once you get over about 1 gigabits, EMC becomes a nightmare. That's why optical fiber transmission becomes critical. By 2040, the vision is for an all-optical communication network inside the car that connects seamlessly to the road and the cloud.
But it's not just about raw speed. For safety, the timing has to be perfect.
It has to be deterministic. That's where technologies like time-sensitive networking, TSN, come in. It guarantees that a brake command arrives exactly when it's supposed to, down to the microsecond.
And this all has to tie into the outside world, into the cloud.
Yes, it's a full vehicle road cloud integration. The system will use edge computing, new wireless tech, and by 2040, even direct high-speed satellite connectivity to ensure the car is always online, always connected to its brain in the cloud.
What's the main roadblock to making a 50 Gbps network a reality in a car?
The sheer complexity of fusing all that information in real time. You have data streams from the car's sensors, from the roadside units, from the cloud. Managing all that without conflict is a huge technical challenge. And yet again, a lack of standardized communication chips that hinders mass production and keeps costs high.
Which brings us to the final piece of the puzzle. We have the design, the hardware, the software, the network. Pillar 5. Simulation, testing, and evaluation. How do you prove this incredibly complex system is safe?
The current methods, relying on expert opinions and old tools, are completely inadequate. The goal is a radical shift to a unified, standardized, and highly automated evaluation environment.
How can you possibly test for every scenario in a one-month development cycle?
You can't do it physically. It has to be done through virtualization and automation. The future is using AI and machine learning to generate and run billions of test miles in a simulated environment.
A digital twin of the entire EEI.
An incredibly high-fidelity one. The scenarios will have to cover everything from single-car autonomy all the way to a fully integrated space-air-ground architecture that includes the satellite links.
So what are the actual targets for this virtualization? How much of the testing moves into the digital world?
The metric is the EEI virtualization rate. For 2030, the target is 90% virtualization, with AI automating 70% of the testing.
And by the end of the roadmap?
By 2035, it's 95% virtualization. By 2040, the goal is a near-perfect 99% virtualization rate, with AI handling 90% of the work. And that final simulation environment has to be powerful enough to test a system running on a 2K TOPS chip communicating at 50 Gbits.
So the test environment itself has to be a supercomputer. But if every automaker has a different architecture, how can they agree on a standard test?
And you've hit on the biggest obstacle of all. The negative cycle pops up again. The sources are clear. The number one barrier is the lack of unified standards for testing.
Everyone defines safety and failure differently.
Exactly. So every validation effort is duplicated, which is massively inefficient and costly. Automakers are reluctant to invest in shared infrastructure, which slows the whole industry down and prevents them from breaking that negative cycle.
So that was just an incredible deep dive into this roadmap. To summarize the journey, we're moving from today's fragmented systems to a fully integrated AI-driven vehicle cloud centralized architecture by 2040. And success is defined by a development cycle of just 1 month. So what does this all mean for you, the future driver and informed observer?
It means the car is truly becoming a software-defined network device. But to get there, the industry has to overcome 3 huge systemic challenges that we saw pop up in every single pillar.
And the first one is about the physical components themselves.
Right, the technical bottlenecks. The industry has to master the domestic supply of the most complex parts. The 2K TOPS chips, the advanced E-fuses, the lightweight aluminum conductors. Without that, strategic risk remains.
The second challenge is the one we kept coming back to, the structural one.
The standardization and ecosystem maturity challenge. This is about finally breaking that negative feedback loop. It requires open, unified standards for software interfaces, data protocols, and especially for testing. Without that, you never get the scale needed for world-class AI.
And the third, final challenge is the human one.
It's talent. The severe shortage of those cross-disciplinary systems engineers who can bridge hardware, software, and the cloud is the single biggest bottleneck to hitting those 1-month development targets. You just can't execute this vision without them.
So this entire massive transformation really hinges on 3 things: attacking core technologies, establishing open standards, and cultivating top-tier talent.
It's a radical industrial strategy. It's setting the stage for a period of hyper-acceleration we've never seen before in the auto industry.
And that brings us to our final provocative thought to leave you with. This roadmap sees cars becoming less like finished machines and more like constantly evolving, networked cloud devices. So if they achieve the ultimate goal, a unified architecture that can be developed and deployed in 1 month, will the concept of a car model year even exist in 2040? What does a 1-week feature update cycle mean for the life cycle, the value, and the very ownership of a device that is never truly finished? Something for you to mull over as you think about the accelerating future of mobility.